So to take an example here, we see an existing test. Okay, browsing, add to cart, selection dialog, checkout, login dialog, login good, purchase dialog, and abandon. So this is abandoning from the purchase dialog box, right? Purchase dialog state. So modified test that we can create here is try to force a continue shopping event while in the browsing state, which is not defined. And then see if you can actually continue on to the purchase dialog and then abandon without it doing something weird. Now, the thing you have to worry about is just because nothing weird happens when you force the undefined event to occur doesn't mean that you haven't set into motion a sequence of events that will result in weirdness later, right? So you have to carry the test through to its logical conclusion to verify that that the right thing has indeed happened. In fact, we've just now seen an example of this where we tried to change the state of the timeout and on the screen, and it didn't change. So well timed. Here's another example, another modified test from the browsing state. Here we see we're going to try to force a checkout to occur, and then there are a number of other ones where we can try to force undefined events to occur while in a browsing state. Okay, now, one of the things that makes it somewhat time-consuming potentially is you don't want to try to cover multiple undefined event condition combinations in any one test, because if something weird happens, then you can't really say why. You don't know that the system's going to remain in any sense testable after you've done something that's undefined, right? And if you're really paranoid about this, of course, you want to actually reboot between each of the tests. For a typical application, that's probably overkill. You'd probably find to just exit the application and go back in, right? Now, the best possible situation here is that these undefined event or event condition combinations are simply ignored, or better yet, rejected with some sort of intelligent error message. Now, there can be security reasons why it might be better to ignore than to reject with an error message, right? If the rejection with an error message is going to give somebody a hint about how to subvert a security feature, then usually you want to simply ignore that, right, and not provide any hints. So for example, when you enter a valid username but an invalid password, most systems will not come back and say that is not a valid password for that username, because that would, in essence, confirm the validity of the username and be providing helpful information to someone who might be trying to break in, right? The more secure approach would be to either ignore it or to come back and say that is not a valid username password combination. So the exact right thing to do can vary, but generally you want the event or event condition combination to be handled in some way that makes sense, and the processing would continue on normally from that point. So it would not have some abnormal termination that would happen a few seconds or minutes later as a result of this weirdness having occurred. Okay, now, sequences of events. Moving on to this issue of testing of sequences of events. There is this concept of what's called switch coverage. Now, things get a little bit complicated here, potentially. Try to keep this fairly straightforward. Switch is basically just another way of saying transition. And the person who defined this, a professor named Chow, for some reason picked the name switch rather than transition. I guess he liked it better. Now, Chow did something else weird, which was instead of referring to switches as the number of transitions, he subtracted one. So if you're going to cover all transitions of length 1, then that's called zero switch coverage. Why? That's what Chow said. That's why he called it zero switch. I don't know why. Obviously, this would have been more comprehensible if you called it one switch for one transition long and two switch for two transition long, but he didn't. So zero switch refers to covering all transitions of length 1. One switch refers to covering all transition sequences of length 2. Now, they have to be possible combinations of transitions, okay? And so what we're going to do to try to identify the possible combinations of transitions, and by possible I mean here defined on the diagram, okay? In other words, we're not going to try to do transitions of length 2 or 3 or whatever that include invalid stuff. That was what the table was for. So what we can do is define a table. Now, the number of rows in the table corresponds at most to the number of states in the diagram. Okay? So here you see, this is the A row, B row, C row, D row, F row. Now you might be saying, well, what happened to the E row? Well, the E row has no outbound transitions. Once you get into the E row, it's like the Roach Motel of the state transition diagram. You check in, but you don't check out. You're there, right? Okay? So you won't need a row in the table for any such state, because any transition that goes into that state, there won't be any exiting transition from it. Okay? So we can leave out the E row. So we have, in this case, 5, which is less than 6. So the number of rows in the switch table will always be equal to or less than the number of states in the state transition diagram. The number, well, let me back up just a second. There are two halves or two parts to the switch table. There is the zero switch part, and in this case, the one switch part. If we were trying to cover all transitions of length 3 or longer, then we would have a third part to this table, which would be the two switch columns. Okay? But because we're interested in this particular example in one transition length sequences or two transition length sequences, we're just going to have zero switch and one switch. Now, in any switch table, the zero switch part of the table will have the number of columns equal to the maximum number of outbound transitions from any of the states. Okay, so in other words, any state, you look at every state, you determine how many outbound transitions there are for that state. The number of states with the maximum number of outbound transitions is going to determine how many columns you have in the zero switch part of the table. Okay? In other words, we've got to make the table wide enough that we can include all of those. Now, to generate the contents of the zero switch side of the